This Kinetics 3 video will start with the integrated rate law. Integrated rate law. And I will give you a little bit of background information on it before I get to that. We looked at first order reactions. And the example that I used several times, N2O5, two of those. This is all gas phase. I'm going to leave off the phase information for this treatment here. Forms 4NO2 plus O2. And remember we said that we could write the rate of this as being equal to negative change in concentration of N2O5, negative because it's a reactant, excuse me, divided by delta T. And then we used this example on the last video, Kinetics 2, and we learned that the rate of this reaction is K times N2O5 to the first power. You may remember that. So specific to this reaction then, we have these two equations, and the next step in the derivation of the integrated rate law is to put them together. So we say negative change in the N2O5 concentration divided by the change in time will be equal to K times N2O5. So we're going to use a little bit of calculus here. And if you haven't had calculus, don't worry about it. I'm not going to ask you for this derivation. So I'll actually put the calculus part in blue. You can ignore it if you want to. There's no problem there. We use the symbol D instead of delta because we're looking at very, very small changes, infinitesimally small changes. So dN2O5 dt, put the negative on the right-hand side, negative K N2O5. The next step is to separate the variables. So we want to put everything with N2O5 on the left-hand side and everything with time on the right. So d N2O5 divided by N2O5 concentration is negative K dt. So the next step is to integrate that, and you use our integral signs. In fact, the K could be, let me erase that last one. Yeah, the K could be, the integral sign could be right there. All right, we're ready to integrate this equation, and we're going to say when time equals 0, the N2O5 concentration is the initial concentration, and when time equals T, then the concentration will be N2O5. All right, we're ready to integrate now, and you may remember the integral of dx over x is equal to the natural log of x. So we'll use that form on the left-hand side. The integral of dN2O5 divided by N2O5 will be equal to the natural log. So put that in a box. That's just one of the laws that we use. So we're going to integrate this, and it'll be ln N2O5 divided by N2O5 initial. So I plugged in the limits, and then this will be equal to negative KT minus 0. So this is going to be the final result here. All right, this is the equation that you want to learn. And don't worry about that derivation. So this is referred to as the integrated equation. For first order kinetics. Okay, so then we can play around with this a little bit. And first thing, of course, you know that the logarithm of n205, this is just the laws of logarithms here, minus the natural log of n205 initial is equal to kt. So you can separate those terms out of the this part right here. Next, we can put the initial term on the right-hand side. So you have ln n205 is equal to, this should be, hold on, that's got to be negative. Yeah, sorry. Negative right there. So then this is going to be negative kt plus ln n205 initial. So this is another form that's very useful of the integrated equation, and that's because this has the form y equals mx plus b. So if we wanted to use the natural log, we could do a graph and we could get the slope, and that would be related to the rate constant and so on. The next thing we can do is look at, again, the first form, natural log of n205 divided by n205 initial, and that is equal to negative kt. That was in the first box. Now we can take the exponential or the inverse log of both sides, or the anti-log of both sides. And so that is done so with the symbol e here. So e to the logarithm of the something is equal to the something. And then on the other side, you do the same thing. So this time it'll be e to the minus kt. So e to the log of the something is equal to the something. And then on the right-hand side is e to the minus kt. Next step would be to rewrite this as n205 concentration. It will be equal to the initial concentration of n205 times e to the minus kt. So e to the minus kt is a decreasing function, so it tends to attenuate the initial concentration until you get some final value. And so you can see here that there's an exponential decay, exponential function there associated with this first order rate law. And here, if you did a graph of n205, your initial point up here is concentration. Your initial point would be, this point would be your initial concentration, n205 initial. And then this is time down here. So you start with the initial concentration, and in time the concentration decreases. And if the reaction goes 100%, then the initial concentration of n205 will go down to 0. And the nature of this curve is exponential. It's an exponential decay. And usually if you have a function, you know, e to the x, that's going to be an exponentially increasing function. But the fact that you get the negative sign in it like that means that it's going to be an exponentially decreasing function. And that's the form that you have right here. All right, good information. If you have a first order data set from your experiment and you plot just concentration versus time, you're going to see this exponential behavior. It's hard from this form to pick a certain time and figure out what the value of n205 is. If you have it in the logarithm form, it's much easier to do that. So moving towards that concept, we can I'll say or here, you can use base 10 instead of base e. So using the law of logarithm, let me do that in red. The logarithm of x is equal to 2.303 times the base 10 logarithm of x. This is one of those laws of logarithms that I went over when I did that session on logarithms earlier. So for this, you can solve for the base 10 logarithm of x. It'll be equal to the natural log of x divided by 2.303. And then go back to your integrated rate law for first order. Natural log of N2O5 divided by the initial concentration of N2O5, and that's negative KT. So we had that before. Now we're going to substitute into, the log x, the base 10 log x for the base e log x. So we'll say, let's see, I guess if we're going to do it this way, the natural log would be 2.303 times the base 10 logarithm of N2O5 divided by N2O5 initial. And that'll be equal to negative KT. And then just divide by the 2.303. So this is base 10 log of x, where this part is equal to x. Excuse me. Negative KT divided by 2.303. All right, and then if we break the logarithm expression into two parts, we can say base 10 logarithm of N2O5 minus base 10 logarithm of N2O5 concentration initial will be equal to negative KT over 2.303. Then we'll take this log concentration initial and put it on the right hand side. So you have logarithm N2O5 is equal to negative KT divided by 2.303 plus logarithm N2O5 initial. All right, so this is the very useful form of the integrated rate law for first order. And this is in the form of y equals mx plus b. And in the case of this equation, the negative k over 2.303 will be equal to m. If you're doing a base 10 plot. So let's go ahead and look at that. If we have some data, we've got time in seconds, concentration, N2O5, and then we can take the base 10 logarithm of the value of the concentration of the N2O5. So start with time is 0. And in our experiment, maybe we had 0.02 molar to start with. The negative log of that number is the logarithm of the number is negative 1.699. Then after 100 seconds, I'll leave off the zeros after the decimal point, 0.0169, and then negative 1.772. 200, we have 0.0142 and negative 1.848. 300 seconds, 0.0120 and negative 1.921. 400, 0.0101, negative 1.996. few more here. 500.0086, negative 2.006, 600, 72, negative 2.143, 700, and then 800. Oops, I think I made a mistake. 400 was 0.86. Next one was 72600. Okay, and then 0.0061, negative 2.215. I don't have a value for that one, but this is negative 0.23, whatever that is. All right, so there's some data from an experiment. And we can graph it next. So we're going to plot the logarithm of N205 versus time in seconds. So we have here, we're going to go to 800, 0, 100, 200, 3, 4, 5, 6, 7, 800, like that. Okay, and then the base 10 log, somewhere in here, negative 2.3, negative 2.2, and up here maybe negative 1.77 and negative 1.699, and points in between. So then we can just pick a couple of data, just two data sets for this, and I will extrapolate for the rest. So pick this data set right here, and then this one, could pick any, I just happen to grab those two. And if you have 100 seconds, then it's negative 0.0169. Did I get that? No, negative 1.772, so it's going to be right there. And then if it's at 700 seconds, it's going to be, the logarithm is going to be negative 2.2, something like that. Okay. You could plot the other points and you're going to get a nice straight line. Okay, so what is the slope of that line? You're going to take the change in y divided by the change in x to get the slope. So it's going to be the change in the logarithm of the concentrations divided by the change in time. So the slope would be m. And we'll take negative 2.215 minus a negative 1.772. And then divide that by 700 minus 100. So the slope here will be equal to negative 7.5, 10 to the minus 4, seconds to the minus 1. Okay, so where did the units come from? You have a change in, wait a minute, hold on. You have change in the log of the concentration. And remember, if it's written as a ratio, the units are going to cancel. So it'll be logarithm of this molar divided by that molar. So the molars are going to cancel. You don't have units in the numerator. In the denominator here, you have seconds. So the slope is going to end up being seconds to the minus 1. All right, and then remember that the slope is defined as negative k divided by 2.303, and that's because we've got a base 10 logarithm plot versus time. And so then you can solve for k. K will be equal to negative 2.303 times the slope. So k will be equal to negative 2.303 times negative 7.5 times 10 to the minus 4 seconds to the minus 1. So k equals 1.7 times 10 to the minus 3 seconds to the minus 1. And we have here that the slope is negative and k is positive. And that's because of the negative sign. Oops, not that one. The negative sign right here. So one is the negative of the other. All right, so we have that for that particular reaction with the N2O5. That's the slope. Now we'll do two examples. I'll start that on a new page. Oops. Whoops. And the first example will be how long would it take if the concentration of N2O5 decreases to 1 times 10 to the minus 2 molar from its initial value of 1.65 times 10 to the minus 2 molar, question mark right there. All right, so your job is to figure out what equation you need for this. And you're given an initial concentration here, a final concentration here, and you know the value of K because we just figured it out. Let me put that in there as well, so just in case you forgot that. K is equal to 7, check that. What happened? Yep, got that wrong. So, K is 1.7 times 10 to the minus 3 seconds to the minus 1. Okay, so then we can go ahead and use our integrated equation here. We've got the rate constant, initial and final concentrations. It would make sense to use that equation. So we can say base 10 logarithm of N2O5 divided by N2O5 initial is equal to negative KT over 2.303. We could use the natural log too. In fact, I always do that, but the way the problem's written in my notes here, it's base 10. Doesn't matter, you're going to get the exact same answer. All right, so you have the logarithm of your initial concentration, no, I'm sorry, your final concentration, 1.0 times 10 to the minus 2 molar, and then divide by the initial concentration, 1.65 10 to the minus 2 molar. Notice how the molars cancel. I was talking about that a minute ago. Negative 1.7 times 10 to the negative 3 seconds to the minus 1 times T, and then divided by 2.303. And for this one, you should practice this logarithm thing. And don't forget that you take the ratio first and then you take the logarithm of the ratio. I do not recommend that you plug log 1 times 10 to the minus 2 minus log of 1.65 10 to the minus 2. It is not incorrect, but students tend to mess it up, just get really wrong answers. Sometimes they take the log of 1 times 10 to the minus 2 and then just subtract 1.65 10 to the minus 2, but you can't. You have to take the log of it. It's much easier to take the ratio here and then take the logarithm of whatever number you got in your calculator there. All right, so then if you do it my way, you get negative 0.217, so you should practice that. And then negative 7.38 times 10 to the minus 4 seconds to the minus 1 times T Solve for t, you have 295 seconds. And you could convert that to minutes if you wanted to, but you don't have to. 4.90 minutes. Like that. All right, so that is the first example. The second example is the same reaction, same rate constant. So if the initial concentration of N2O5 is 1.65 10 to the minus 2, comma, what is the concentration after 825 seconds? And also it's the same K, 1.7, 10 to the minus 3 seconds to the minus 1. So it's the same reaction, the N2O5 reaction at the same temperature. So the rate constant K is the same. All right, in this case, we're going to, let's think about that for a minute. You're given the initial concentration and you're given the time and the rate constant. So if you used the integrated rate law again, natural log of N2O5 divided by N2O5 initial is equal to negative KT. Would it make sense to do that? So you've got the time, 825 seconds, rate constant, 1.7 10 to the minus 3. You're given your initial concentration right here, and your job is to figure out what is the concentration after 825 seconds. So it would be appropriate then to use the integrated rate law, the way we have it here. And let's see, I think in this one, I went ahead and just used natural log. You can go back and forth between them. You can stick to the base 10 log with the 2.303 if you want to do that. But just to give a little variety here, let's switch it up. All right, now I'm going to call this one method 1. We'll contrast that to method 2 in a little bit. So here we are going to say the natural log of N2O5 divided by 1.65 times 10 to the minus 2 molar equals negative 1.7 10 to the minus 3 seconds to the minus 1 times 825 seconds. And we will say e to the logarithm of the something is equal to the something, which is N2O5 divided by 1.65 10 to the minus 2 molar. And then this will be equal to e to the minus, and if you take the product of those two, you get 1.40. So we're getting closer here. Next step is multiply the initial concentration. So you're going to get N2O5 will be 1.65 10 to the minus 2 molar multiplied times e to the minus 1.40. So you put the 1.40 in your calculator, take the negative of it, and then take the inverse natural log of that number for the next step here. So then you solve and you get N2O5, which is, well, one more step here, 1.65 10 to the minus 2 molar, and then if e to the minus 1.4 is 0.247, so you should just check that and make sure you get that. And then N2O5 is equal to 4.06 times 10 to the minus 3 molar. Okay, so that's fine. The trick here is knowing how to take the inverse log of both sides. And practice makes perfect on this one. Would I ask you for a question like this one? The answer is yes, because what you're doing here, if you look back to how it was set up, you're solving for x in the argument of the logarithm. And that's the hardest thing that we're doing mathematically anyway. All right, then we have method 2, because I know you guys will want to split that log. And so method 2 here would be the natural log of N205 minus the natural log of 1.65 10 to the minus 2 molar. So in other words, way up here. You start from here and then you do that. And so then that would be equal to negative 1.40. And then you can calculate this value. So this would be equal to the natural log of N205 minus 1.40, and that'll be negative 1.40. Nope, that's wrong. Negative 4 point. What happened? Let's see. Let's be negative 1.40, and then this. Making a big mess here. Sorry. And then this term we're going to put on the other side, and that is plus the natural log 1.65 10 to the minus 2 molar. So then you've got negative 1. Yeah, so we get rid of that. Yeah. Okay, and then we have natural log N205 is equal to negative 1.40 minus 4.10. Combine those, you get natural log N205 negative 5.50. And then take e to the logarithm of the N205. That'll be e to the minus 5.5. So then on the left you get N205. And on the right you get e to the minus 5.50. And N205 equals 4.06 times 10 to the minus 3 molar. So then you have method 2 is where you separated those two parts of the logarithm. And then method 1, you did not. So this is the result of method 1. This is the result of method 2, and you get the exact same result. Sorry, my throat's dry today. All right, you cannot just read this. You can't just watch what I'm doing. Write down these two problems with all the data that you need to solve it, and then sit separately with your page and write it out. Solve it by yourself. You just can't walk into a test or a quiz cold with this problem. You've got to try it yourself. And you got to try it a bunch of times until you're really comfortable with it. And the group activity that we're going to do on this is very similar. The first couple of questions are of this nature here. So, all right, moving on then, we have equal to Stealth mode, what's that? I have second order. Second order integrated rate law. And we start with the rate of the reaction in this, well, hold on. Get out of my inspector there, stop. Ugh. Okay, sorry. So we're gonna have the reaction of A going to B, something like that. And we'll say the rate of the reaction is negative change in concentration of A divided by change in time. And then, so that's the first way we talked about the rate of the reaction. The second way would be particular for the second order. So we'll say rate is equal to K times A squared. Now, how did we get that? We did the experiment where we doubled the concentration of A, and we found that the rate of the reaction quadrupled. So that's that isolation method that we went over in the first Kinetics 1 video. Okay, so there's two ways to write rate, and if we want to do a little calculus on it, we will equate them. There we go. So we're going to say, I'm going to combine them, and just put the negative on the other side. Change in concentration of A divided by change in time will be equal to negative Ka to the second power. And we'll switch to our calculus symbolism. D instead of delta, dA divided by dt will be equal to K times A squared. The next step is to separate the variables. So you put everything with A on the left-hand side and everything with time on the right-hand side. Then we can do an integration to get rid of those D's, basically. And so maybe you remember that the integral of dx over x squared is equal to negative 1 over x. So we'll use that on the left-hand side. All right, so plug in, and we will have 1 over, oh, I forgot to put the limits in too. So when time equals 0, the concentration of A is A initial. When time is t, the concentration of A is A final, or A at that time. All right, then we do the substitution, we do the integration, and we will get 1 over A, and that is going to be negative. Our limits are going to be between A initial and A. This will be equal to negative KT minus 0 minus 0. So then you have negative 1 over A minus a negative 1 over A initial equals negative KT. So negative 1 over A plus 1 over A initial, negative KT. Negative 1 over A is equal to negative KT minus 1 over A initial, and multiply everything by negative 1. So you have 1 over A is equal to KT plus 1 over A initial. Very important equation. Forget about the calculus, just look at what's in the box here. And so this is your integrated equation for second order. All right, no logarithm, so it makes it a lot easier. And if you have a graph, 1 over a versus time. So how do you get 1 over a? Your data is going to be time and concentration, right? You have all these data points. But if you're going to plot 1 over a in your table, you have to take the reciprocal of each one of your concentrations there and calculate those, and then that's what you're going to plot right there. So 1 over a concentration versus time. This is a linear relationship. This is, again, y equals mx plus b. And in this case, you're going to have a straight line, linear relationship. This point right here will be 1 over a initial. And then the slope, it's got a positive slope. And you can look at the equation. The slope will be equal to k. So it's much easier than the logarithm form for first order. All right, so let's do a quick example for this one. You have, you have the reaction NO2 forming 2NO plus O2. This is second order. And K equals 0.775 molar to the -1 seconds to the -1. Notice that K for first order in the last couple examples, the units were seconds to the -1. So if you have a rate constant second to the -1, you know it's first order. If it's second order, the units are going to be molar to the -1 second to the -1. If you're given those units, you know that you have a second order reaction. Okay, so let's say your initial concentration is 0.0030 molar. What is the concentration of NO2 after 655 seconds? Okay, you know it's second order. You've memorized the equation for second order, the integrated equation. And we have our initial concentration right here, 0.0030. The value of K, 0.775. And we are given time, 655 seconds. We can calculate 1 over A and then take the reciprocal of that to get the concentration A, which is the concentration at time t, 655 seconds. So for this one, we have 1 over NO2 is equal to 0.775 molar to the -1 second to the -1 times 665 seconds. And then you have plus 1 over your initial concentration. All right, and then on the right-hand side, oh, I don't have the details of this. I just have the solution. So you can practice this on your own. The answer is 0.0012 molar, or 1.2 times 10 to the -3 molar. Okay, so the next topic is zero order kinetics. What we find from the experiment is that the rate is independent of concentration. So you can change the concentration, you can change your initial concentrations, the rate of the reaction stays the same. We have our two expressions here, rate equals negative dA dt, and in this special case we have rate is K times the concentration to the 0 power, 0, a to the 0 is going to be equal to 1, so this will be equal to K. Combine those two, and we have dA dt is equal to negative K. Then separate our variables. dA is equal to negative K dt. Integrate 0 to t, A initial to A. And so then we're going to have, let's see, integrate dA, it'll be A, so A minus A initial is equal to negative KT, or A is equal to negative KT plus the A initial concentration. So this is the integrated equation for zero order. So we have, for this particular example, the rate is independent of the concentration, and then this kind of very simple equation, the integrated equation, simple integrated equation. And if you just take a plot here, this is y equals mx plus b as well. So a versus t, it's got a negative slope, and so the graph should look like that. Just concentration versus time is going to be linear. And the slope here will be equal to negative K. All right, there we have it. And I think, yeah, I guess we'll go ahead and do that calculation. Next example here, determine the rate constant K if the initial concentration is 4.0 molar after 60 seconds. The concentration is 1 molar. So you use the integrated equation. A is equal to negative KT plus A initial. In this case, we have 1.0 molar is equal to negative K times 60 seconds plus 4 molar, and solve for K, it's 0.050. And the units here, you would have to subtract 1 molar, subtract 4 molar from 1 molar to get negative 3 molar. And then you're going to divide by 60 seconds. So the units are going to be molar times seconds to the minus 1. And that would be the answer for that one. All right, so the next part of this is the half-lives of the reaction. I think I'm going to do another video for that. I don't want this to be too long. I might have trouble booting it up. So I'll stop here.